Let's move forward into chapter 2 of Tom Stoker's book on Introduction to Climate Modeling and look at a spectrum of climate models and do one of the simple energy balance models, and also look at how we evaluate models, how good they are. In the forecast models, often it tends to be simple. You make a forecast, and after the forecast period has passed, you just look at the skill or the correlation of the forecast versus what actually happened. If the forecast is reasonably high, let's say above 0.6, then it's considered usable information and a skillful forecast. So I hope I'm not tinkering with the sound here. So model hierarchy and simplified climate models is the second chapter. Immediately we'll look at a table of models here. Hierarchy of coupled models for ocean and atmosphere with some examples ordered according to the number of spatial dimensions considered. So is it zero-dimensional, averaged over the whole globe in vertical and horizontal, or is it one-dimensional, two-dimensional, three-dimensional, and so on? The direction of dimension is specified in brackets: latitude, longitude, and vertical. 2.5D corresponds to several two-dimensional ocean basins like the Southern Ocean. EBM stands for Energy Balance Model. QG, we already did energy balance, so now we look at it from the perspective of modeling. QG is the quasi-geostrophic, atmospheric general circulation model, ocean general circulation model, sea surface temperature, and some example models and their authors are given in italics, and the gray shaded area contains climate models of reduced complexity, what we referred to already as Earth system models of intermediate complexity. Obviously that definition is not very objective. This just permits integrations over very long periods because of the simplifications into intermediate complexity, and you can make large number of simulations, what are called ensembles. Ensembles are best thought of as potential realizations that could have happened. For example, we talked about weather forecast starting from initialized conditions going forward, and let's say the nature is starting every day at some point and integrating forward and giving you the outcome that you see as actually what the weather that you experienced in terms of temperature, rain, humidity, cloudiness, winds, whatever. And in the model you are not likely to get exactly the same initial conditions, so your forecast may be off by a little bit in addition to whatever model problems there may be. To cover the potential range of outcomes that Mother Nature would have provided, you just perturb the initial conditions or do some other perturbations and integrate forward multiple realizations, and if the model is good, then the ensembles of the model simulation tend to cover what actually happens in nature. And this kind of ensembling is also done with multiple models, and evidence suggests that ensembles and multi-model ensembles typically tend to give more skillful forecasts and realizations. So we already saw the gray bands in the previous podcast of multiple models and their mean. So this is the idea of ensembling, and now there are ideas of large ensembles which basically tend to remove random errors, and only systematic or systemic errors tend to remain. So it gives us a chance to improve our forecasts or projections. So here we are. Dimensions: atmosphere 0, 1, 2, 3, and the ocean also has dimension 0, 1, 2, 3. And energy balance models are point models, so they have averaged out everything and just looking at energy coming in, energy going out, and maybe add a layer which would make it surface, atmosphere, and space. Bipolar seesaw, so Tom Stoker and Johnson. Dynamical systems, so those are called as Salzman models. So these are all zero-dimensional models. Pulse response models are where you perturb the system with a pulse and look at the response. There are some assumptions involved here that it's a linear system, which has to be confirmed from more realistic and sophisticated models. Neural networks are basically taking observations of, let's say, precipitation and temperature, and kind of doing relations between them to make either forecasts or to explain the variability of temperature and rainfall, or their covariability, and various ways in which they could be used for processes. If you keep the atmosphere to be zero-dimensional, you can have one-dimensional, two-dimensional, or three-dimensional oceans, and you can have Ekman models where only the wind-driven currents are considered in the vertical, so it's only the z dimension. Global mixing models, so you assume the mixing is only happening in the vertical, not related to horizontal gradients of temperature, salinity, density, vertical shear, horizontal shear, and so on. Advection diffusion models, so again, you know what advection is. If it's one-dimensional, then only vertical advection is possible. Two-dimensional, you have thermohaline models, which looked at how ocean creates a thermocline and maintains it in the context of the forcing and vertical exchanges and so on. Wind-driven flow, latitude, longitude, deep ocean, latitude, longitude, and if you go to three-dimensional ocean, of course you have the complete ocean general circulation model if you're solving the full so-called primitive equations or Navier-Stokes equations with rotational terms. So momentum, mass, energy, thermodynamics, and so on. If you go to one-dimensional atmosphere, you can get energy balance models, which can be like zonally averaged latitudinal diffusion models, radiative convective models, so they do vertical balance as well, one-dimensional. Ocean is kept zero-dimensional. There are hardly any one-dimensional atmosphere and one-dimensional ocean models, except maybe Hezi Gildor and Adam Sobel may have done a MJO model where they had such a one-dimensional model for the ocean and the atmosphere, but please check. With one-dimensional atmosphere, two-dimensional ocean, you can get ocean, which is latitudinal and depth, and energy balance model for the atmosphere. That's a particular model by Tom Stoker, Lawrence Mizak, and Wright. EBM, Norton Crowley, statistical dynamical atmosphere and diffusive ocean model. You can increase the ocean to ocean statistical dynamical atmosphere, and OGCM plus EBM, OGCM plus quasi-geostrophic model. AGCM forced with SST, as we said in weather forecast. We assume ocean is evolving too slowly to affect the atmosphere on a few days, so we typically tend to prescribe the sea surface temperatures in some way for the future, either persisting the current temperatures or doing some other way of prescribing SST. So there the atmospheric general circulation model is a full model. They have served a lot of purposes in terms of learning how atmospheric processes work, because as opposed to the coupled atmosphere ocean GCMs, AGCMs are very cheap to run computationally, and you can make many runs or many long runs with prescribed SSTs. AGCM plus mixed layer, where ocean is only represented with the top layer where some kind of a thermodynamics and advection or heat transport happens. They also provide lots of realistic simulations of coupled behaviors where ocean's role cannot be ignored, unlike here. AGCM plus slab ocean model. Here slab means in the mixed layer model model, the upper layer of the ocean can change in thickness either in time or in space and time, whereas in a slab ocean model it's fixed. So that makes a difference in terms of the heat capacity and the amount of heat being moved and so on. Atmosphere, ocean, general circulation models, many exist now in the world. CCSM3 from NCAR and HADGEM from the UK Met Office are just a couple of examples. Okay, here is an example of the Bern model that we already looked at. Concept and geometry of the Bern 2.5 model, one of the first climate models of reduced complexity by Tom Stoker. Ocean currents are averaged zonally, so in the longitudinal direction, and are simulated by 3 basins connected in the south, so it's called category 1 and 2 here. I won't go into those details. Thanks to strongly simplified depiction of the climate system, simulations spanning over 10 to the 6 years, so million years can be carried out. So Pacific Ocean and Atlantic and Indian Oceans are prescribed with various latitudinal extents, and they are all connected by the rendition of the Southern Ocean. So there are exchanges between the atmosphere and the ocean. There is sea ice provided. There is some representation of the biosphere. These are very useful for process understanding, especially on long time scales, and often the most critical results that come out of it may have to be verified in some way by more sophisticated models. So they are very instructive in telling us about lots of things about, for example, the time scales that emerge on long periods when the Southern Ocean is allowed to be active and connecting to these oceans. So things like thermohaline circulation that we briefly mentioned, where North Atlantic deep water and Antarctic intermediate and bottom waters form, and then thermohaline circulation occurs through these, and on millions of years of time scales based on various forcings prescribed, orbital forcings, tectonic forcings, freshwater forcing over the North Atlantic to simulate glacier melts and so on and so forth. So lots of interesting results have been produced by this paper. In general, the full atmosphere, ocean, general circulation models, I mentioned by hand that we take the sphere and we split it into grid boxes. So here we are. Here is a sphere, and you look at any place. You have mountains, land, and ocean. So you look in the ocean, you have sea level here and the continental shelf. Deep floor is here. Ocean also has mountains in them, so you represent everything with boxes. Typically the upper ocean is much more active, so we tend to put higher resolution. So you can see that the vertical scale of these near surface boxes are much higher than the bottom boxes, because the deep ocean hardly moves. It keeps the heat, releases the heat, takes the deep water, converts it to surface water, and so on. So we try to use what we know about the processes to optimize the distribution of the resolution in the models as well. And similar things happen in the atmosphere near the surface planetary boundary layer and lower troposphere, with lower resolution in the upper troposphere and stratosphere, and so on. So various kinds of assumptions happen, and the 3D grid boxes carry variables like greenhouse gases, dust, water vapor, and then there is energy coming in, energy going out, clouds are being formed, heat is being transported, evaporation, precipitation, etc. happen. So that's a very quick run through these, but you get the idea that between each grid box there is exchanges of fluxes of energy, momentum, mass, and the best test is, of course, as we said, if we give it the energy from the sun and prescribe the minimalist things that need to be prescribed, like the continental configuration, the mountains, etc., then how does the solution look? Does it look realistic in terms of the distribution of rainfall, winds, trade winds versus mid-latitude westerlies, how the ocean circulation looks, how the distribution of deserts look, and so on and so forth. So that is about validation of the models. So maybe I will leave this here and come to validation of the models in the next podcast. But you get the idea that models have a large spectrum of dimensions, complexities, process representations, and one has to be very keenly aware of what the model is capable of doing, so that when you use it, you know what you are getting, that you are actually representing the key processes for the exploration you are making of the climate system. Okay.